Hello, and welcome to our senior project presentation. We have been working with our advisor, Dr. Safe, and Niagara Bottling to improve the overall equipment effectiveness at the Rialto plant. My name is Caroline, and the rest of my team members are Christian, Angelo, Nick, and Raven. We are going to spend the next 12 minutes covering the OEE, machine quality, reliability analysis, CIP process, and lean implementation for one of Niagara Bottling's beverage lines. Working with Niagara has been exciting. It is a fast-paced, automated facility that produces millions of bottles a day. They are expanding and continuously improving every day with over 30 plants across the country. The Rialto plant has 4 water lines that were built in 2014 and 3 beverage lines that were built in 2016. We will be focusing on the beverage line 5. I will now be passing it on to Angelo to talk about our problem statement and project plan.
Thank you, Caroline. For our project, Niagara has requested that our team focuses on 3 different things: decreasing the CIP operator process time, decreasing the downtime of the labeler machine, and improving overall operator performance. To be able to quantify the improvements we will be implementing, our team will be using overall equipment effectiveness as our key performance indicator. Comparing the initial OEE to the new OEE will indicate the impact of our changes to the plant. Along with OEE calculations, we will also conduct cost analyses which will further highlight the impact of our changes. I will be now passing it on to Raven, who will further explain overall equipment effectiveness.
Thanks, Angelo. So the overall equipment effectiveness, or OEE for short, is calculated by multiplying the availability, performance, and quality of a machine, which in our case is the labeler. When calculating and improving the OEE, we calculated an improved availability as a function of MTTF and MTTR, performance as a function of the total count of items produced, runtime of the labeler, and ideal cycle time, and quality as a function of the total count and good count of items produced. Having said that, through using data provided by Niagara Bottling's Rialto plant, we found that the initial overall equipment effectiveness was 0.58. Now, Christian will talk about the labeler machine's quality.
Thank you, Raven. We analyzed the labeler process variability for about 7 months using quality control charts and determined that the proportion of defective units was 3.49%. To put that into perspective, every week Niagara Bottling produces about 4 million bottles on line 5. Therefore, the amount of bottles going to scrap would be almost 140,000 bottles a week. In order to understand the variability of the process, we needed to investigate. In our observations, we learned that the main cause of the defective units was because of excess glue on the label applicator. The operators on the line have the responsibility of cleaning the machine. However, due to their high workload, the labeler machine received inconsistent maintenance. With this in mind, our team has proposed a sanitation supervisor that will not only assist with cleaning the labeler when needed, but as well as other machines. For our proposed solution, we decided to do a cost analysis to see how much money was lost due to defects during our 7 months of observation. We first simplified the materials to manufacture a generic bottle and calculated that the total cost of material waste across our 7-month observation was equal to about $126,000. In contrast, the sanitation supervisor will work part-time during the night shift where assistance is needed the most. They would require simple cleaning supplies with a special machine cleaning solutions as its major cost. This cost was estimated to be around $20,000. Finally, what we see here is a visual comparison between both costs. It is important to note that since Niagara Bottling has different customers that all require different bottle sizes, the cost would increase or decrease depending on the PET plastic content. As we see in the chart, hiring the sanitation supervisor would be cheaper than suffering losses due to defective products. For our quality improvements, we estimate that the proportion of defective units would drop from 3.49% to 1.94%, which is about a 45% decrease in defective bottles produced. I will now be passing it on to Angelo to talk about reliability.
Thank you, Christian. Conducting a reliability analysis is an efficient method to calculate availability, which in our project is defined as the time the labeler in line 5 is capable of operating relative to the scheduled hours of production. In order to find this, the mean time to failure and the mean time to repair are needed. In order to calculate these 2 times, we looked at the labeler's own failures as opposed to external failures. There were 29 different failure modes in total from a 7-month span, which also included their total monthly downtime, runtime, and occurrences for each failure mode. With all the data previously stated, we are able to calculate the mean time to failure and mean time to repair, or MTTF and MTTR respectively, for each month. Once this was finished, we can then find the average MTTF and MTTR across the 7 months, which was found to be 24 minutes and 45 seconds and 5 minutes and 48 seconds. With these 2 values, we can then calculate the availability across the 7 months, which is equal to 81%, which means that 81% of the time across the 7 months the labeler was operating and 19% of the time the labeler was being repaired. To improve the availability of the labeler, we first looked at 9 significant failure modes that occurred during the 7-month span. From the 9 failure modes, our team focused on the 3 most important failure modes. We decided on what is most important based on the total occurrences of that specific failure as well as its total downtime. I will now be passing it on to Nicholas, who will further explain how we improve the availability of the labeler by implementing preventative actions.
Thank you, Angelo. For our financial analysis, our goal was to increase availability. This is achieved by increasing mean time to failure while decreasing the mean time to repair for the top failure modes in the labeler found in our reliability analysis. By understanding the causes of the failures, we recommended preventative actions through the integration of new or additional hardware and software. After analyzing what upgrades would be beneficial to the production, we calculated an economic analysis to determine if these improvements are profitable. For each of the failure modes, we recommend the following preventative actions. In Failure 1, we recommended integrating pre-programmed buttons of different beverage types on the HMI screen that would adjust the line for the next beverage being made. In Failure 2, we recommended the integration of a robotic arm that removes the glue buildup depending on the number of bottles being produced. And in Failure 3, we recommended updating to a new software that would automatically adjust the text on labels to the current date and the beverage being made. In our economic analysis of having upgrades with a 15-year lifespan with installation costs, a reduction in operators, and a decrease in failure modes, we calculated 2 different outcomes for the potential cash flow. Our optimistic calculation calculated a 40% reduction with a positive cash flow of approximately $448,000 per year, and a pessimistic of a reduction in failures by 10%, yielding $144,000 per year. Now I will be handing it off to Raven.
Thanks, Nick. Because Niagara Bottling creates many types of beverages, their filler machines need to be properly cleaned between each drink in order to prevent cross-contamination. In order to do this, Niagara has the 5-step cleaning in place, or CIP, process. Niagara has noticed, however, that the CIP process has been taking longer than usual, and so they've requested that we improve the operator portion of the process to improve how long operators take to initiate and end the CIP process. To do this, we performed a failure mode, effects, and criticality analysis, or FME-CAW for short, to identify and rank the CIP process's failure modes, which are ways in which something may fail. When doing the FME-CAW, each step was ranked by the respective risk priority number, or RPN, which takes into account the occurrence, detection, and severity of each step's failure modes. After calculating these RPNs, it was found that 4 steps' RPNs were significantly larger than the rest, meaning that these 4 steps put the CIP operator at a much higher risk of making a mistake that would be significantly more damaging to the CIP process than other steps. Using the FME-CAW results, suggested courses of actions to combat these 4 process steps failure modes were made. It was found that these failure modes could be combated by surveying operators to see why they may not follow the 5-step CIP SOP, revising the CIP SOP, improving and increasing the amount of operator trainings, adding a stylus to any touchscreens, and adding more visual aids and reminders, like having a job aid behind the filler machines and having a visual aid that reminds operators to turn the capping heads off. Now, Caroline will talk about the lean implementations that were made in the next slide.
Thanks, Raven. Prior to 2021, Beverage needed help on implementing 6S, a lean methodology that stands for sort, shine, set, standardize, sustain, and safety. Our team decided to label all cleaning tools and add an extra clean station to line 5 to reduce unplanned downtime. We also labeled where raw materials should be staged to eliminate safety hazards on the production floor. To help sustain 6S, I created a CIL board and a communication board. CIL is an acronym that stands for Cleaning, Inspection, and Lubrication. It comes from the lean thinking concepts in the Toyota production system based on eliminating waste. A CIL board is a simple and flexible audit system that can be set up in a matter of minutes. It is used to visually audit autonomous maintenance tasks, increasing operator knowledge on equipment and emerging issues before they become failures. The purpose is to clean to inspect, inspect to detect, detect to correct, and correct to perfect. The communication board is where anyone working on the line can be the requester and has the opportunity to report an issue. This board gives all shifts visibility on the daily OEE, weekly, and monthly highest contributors of unplanned downtime. Now on to Raven to talk about the future OEE.
Thank you, Caroline. Because the proposed changes have not yet been implemented to the line, our team made educated estimations on what the availability, performance, and quality values would be once our suggested changes would be made. We made these estimations by removing any of the defects or failure modes that the implementations would target, and once we made these estimations, we calculated that the new OEE would be 0.68. After calculating the new OEE, we compared this to our initial OEE and calculated the percent increase. Through this, we found that the OEE increased by 18.08%. Additionally, for our recommendations, we estimate that Niagara would save an optimistic amount of about $500,000 and save a pessimistic amount of about $203,000. Now, Caroline will wrap up our presentation with our conclusion.
The OEE was a metric that encompassed many components. We worked on quality, maintenance, reliability, and performance to improve Line 5. We focused on the Line 5 labeler because it was one of the top 3 contributors for unplanned downtime. When taking into account our suggestions, we estimate that the OEE would in fact increase. As a team, we'd like to give special thanks to the IMU department for teaching us all that we've learned, to Dr. Say for being our advisor and for helping us so much throughout this entire process, and to Niagara Bottling for helping us gather data and for giving us this opportunity to work with them. We appreciate you all. Thank you for your time. Any questions?